This is the 2025 AP Statistics FRQ questions. I'm going to be going through number 6, and again, this is a sample answer, how I would answer the question if given the problem. So number 6 says, Stefan, a psychologist, conducted a study to investigate the effect of time of day on reading comprehension in children. 100 children volunteered with their parents' consent to participate in the study. 50 of the children were randomly assigned to read a story at 9 a.m. and then answered 25 questions about it. The remaining 50 children were assigned to read the same story at 3 p.m. and answer the same 25 questions. The reading comprehension for each child was measured by a reading score, which was determined by the number of questions that were answered correctly about the story. Stefan is interested in comparing the mean reading scores for 2 times of day. Table 1 shows the results of Stefan's study. Stefan found the conditions for inference were met and conducted a 2-sample t-test for difference in 2 population means. Let mu-am represent the mean reading score for all children similar to those in the study who would read the story at 9 a.m., and let mu-pm represent the mean reading score for all children similar to those in the study who would read the story at 3 p.m. Stefan's hypotheses are shown. The null hypothesis is that mu-am is equal to mu-pm, and the alternative hypothesis is that mu-am is not equal to mu-pm. Part A says the p-value for Stefan's hypothesis test was 0.002. State an appropriate conclusion at the 5% significance level for Stefan's test in the context of investigation. Justify your answer. So for Part A, we would say since 0.002 is less than alpha equal to 0.05, we reject the null hypothesis and have convincing evidence that there is no difference in mean reading scores for the children who read in the AM versus the PM. Part B says, explain why it was appropriate for Stefan to conduct a 2-sample t-test for difference in 2 population means instead of a paired t-test for the population mean difference. So answering Part B, I would say it is appropriate to conduct a 2-sample t-test for the difference in means instead of a paired t-test for mean difference, since the scores came from 2 independent groups using random assignment. Okay, let's look at Part C. Part C says researchers are usually interested in the practical importance of the results as well as the statistical significance of the hypothesis test. The practical importance of the results indicate whether the observed results are meaningful in real life. For example, in an investigation of the height of two groups of students, a difference in the two group means of 3.8 inches is much more meaningful or has more practical importance than a difference in the two groups of means of only 0.2 inches. One indicator of practical importance is effect size. A common method for measuring effect size for the difference in two groups means is Cohen's d coefficient. Cohen's d coefficient compares the absolute value of the difference in the means of two groups to the pooled variability of the observed data values for the two groups. Cohen's d coefficient can be calculated using d is equal to the absolute value of x1 bar minus x2 bar divided by s sub p, where s sub p represents the pool standard deviation of represents the pooled standard deviation, x1 bar represents the sample mean for the first group, and x2 bar represents the sample mean for the second group. When the sizes of the groups are equal, S sub p is calculated as S sub p is equal to the square root of S1 squared plus S2 squared divided by 2, where S1 represents the sample standard deviation for the first group, and S2 represents the sample standard deviation for the second group. Consider the summary statistics from Stefan's study in Table 1. Part 1 says calculate Cohen's d coefficient for Stefan's study and show your work. So here, it's very nice because they give you the formula for Cohen's d coefficient here. And they even tell you what S sub p, that formula is, so you don't even have to remember how to calculate a pooled standard deviation. So it wants us to use the values up in Table 1, so that's these values up here. Okay. And I'm going to go ahead and right here when I have space, I think I have a little space right here, and go ahead and answer C part 1. So we have D. D is equal to the absolute value of x1 bar minus x2 bar divided by the standard deviation pooled. This is, here I'm just plugging in that formula that they gave us. And then I'm going to start plugging in all the numbers from the table. So it doesn't really matter which one you're labeling 1 or 2 because of that absolute value. So I have the absolute value of 15.2 minus 17.9 divided by the square root of 4.12 squared plus 4.43 squared, all divided by 2. Putting that into my calculator, I get 0.631164. So that is Cohen's d coefficient. Let's see what part 2 wants us to do. It says higher values of Cohen's d indicate greater practical importance and lower value of Cohen's d indicate less practical importance. Typically, we use the intervals listed in Table 2 to help interpret practical importance. So based on our answer for part 1 and C, describe the practical importance of Stefan's results in context. So since we got 0.631164, we know that falls within this interval here, which means that Stefan's result is somewhat meaningful in real life. So how I would answer this officially for C part 2, I would mention that calculating Cohen's d coefficient we got D equal to 0.631164, which falls in the somewhat meaningful in real life category. The difference of means of mu of x1 bar minus x2 bar is equal to mu1 minus mu2, which gives us 17.9 minus 15.2, which gives us 2.7. Okay. This implies that the results found in the reading score experiment is somewhat meaningful in real life. Okay, so that was part C. Part D says, suppose the results of Stefan's study, summarized in Table 1, instead had a standard deviation for 9 a.m. reading scores S1 and a standard deviation for 3 p.m. reading scores S2 that were both greater than 4.43. Assume the group sample sizes and the means are not changed. Part 1 says, would the Cohens D coefficient in this new situation be smaller than, larger than, or the same as the Cohens D coefficient calculated in Part C, Part 1? Explain your answer. So here is Part D, Part 1. Okay. So first we have to think, if standard deviation was changed for both of these and both of them were to be greater than 4.43, that means the denominator as a whole would get larger. And when our denominator gets larger, our overall fraction gets smaller, which means Cohen's D coefficient would be smaller than what we calculated in the prior section. So to write that, I would say if the standard deviations were changed for both groups to be greater than the original, then Cohen's D coefficient would be smaller than what was calculated in Part C, Part 1, since we would be dividing by a larger number. Okay, Part 2 says, does the Cohen's D coefficient described in Part D, Part 1, indicate that Stefan's observed difference in the means in the new situation would have more practical importance or less practical importance, or the same practical importance as what was originally determined in Part C, Part 2? Explain your answer. So to me, since Cohen's d coefficient would be smaller, since we're increasing the denominator, which would overall decrease that Cohen's d coefficient, then I would say that there would be less practical importance than what was calculated in C Part 2. And remember, in C Part 2, we said that there was somewhat meaningful significance in real life, but if we decrease that value, we run into the situation where we could end up decreasing the practical importance and following in the interval that states not very meaningful in real life. So how I would state this, so this is D Part 2. Since Cohen's d coefficient would be smaller, then we would have less practical importance than that found in C Part 2.